Hello, I'm Jack. Welcome to my channel, Practical Programming with Dr. Su. In this video series, you will learn everything you need to get started with WGPU graphics programming in Rust. In the last video, I explained how to set up the development environment for building WGPU applications in Rust. This is the third video lesson. Here I'm going to show you how to build a simple WGPU application and this development environment. That is, we want to create a colorful triangle here, like this. This triangle with different vertex colors. You can see 3 vertices has different color RGB. Here, we will use the git tool to clone the source code used in the last example. Now we start Visual Studio Code directly from Windows Start menu. This is the Visual Studio Code interface. Now let's start a new terminal window. In this window, we cd into the code folder, cd code, and then make a new folder called WGPU03 and cd into it. Now we can clone the source code used in the last video with the following command: git clone WGPU02 used in the last video. So from this link you can download all the source code used in the last video. Here we put a space after this comment and a period. This will place all our source code in the current folder. Now run this command. Okay, we can check direct. So you can see all the source code indeed in this folder. Now open this folder from Visual Studio Code. Open folder code WGPU03. Contains the source code used in the last example. The WGPU program consists of 2 parts. One is the control code written in Rust, and the other part is the seeder code run on the GPU. Here we will use the official WebGPU seeding language called WGSL to write our seeder code. Before writing our seeder program, we want to install a WGSL extension in Visual Studio Code. Click this extension link. Search for WGSL. The first one, WGSL, is a syntax highlight for WGSL file. So you need to install this extension. In my machine, I already installed this extension. So you should click the install button to install this extension. Okay, I suppose you already installed WGSL extension on your machine. We now begin to write our seeder code. In the src folder, we add a new file called seeder.wgsl. In this file, we add some code into it. From this code, you can see that there are 2 seeders here. One is vertex seeder, and another one is a fragment seeder here. The fragment seeder, you can see this is vertex, this is a fragment. Here we first define VOutput structure that includes 2 fields. One is the V color, which represents the output of vertex color. And the other one is the built-in position. Inside VS main function is a vertex main function. Yeah. We use a floating point vector 2. You can see vector 2 to define the 3 vertices of our triangle. You can see the 3 vertices here. This is the vertex positions of our triangle. Here, a vector 2 represents a 2-dimensional vector. We also create a color for each vertex, you can see three colors here. Use vector 3 that represents RGB color components. The first color is 100 is red, 010 is green, and 00 and 1 is blue. So they have three vertices have different vertex color here. Here you can see our main function returns out, which is a type of V output structure type. You can see here we convert the position and the color into vector 4 vectors by setting the Z component to 0, W component to 1 here. This is because WGPU API always using the 4D vectors to render 3D graphics objects. So we have to convert them into the vector 4 vectors. The fragment shader, the main function we call the FS main. Here it takes, we output the structure. Here we define here as its input argument and set its return value to V color. This is the output vertex color from vertex shader. So this is the shader we are going to use when we create our colorful triangle. So now we can save this file. Next, we will use the Rust to write WGPU control code. Now, from SRC folder, open the min.rs file. Open this file. Now we need to replace its content by the new code. Here we first create async run function because the WGPU API is async when interacting with the GPU. Inside this function, we define an instance. You can see the instance using the backend called Vulkan to create a new instance. But here we can also use DirectX 12 because our AMD graphics card supports both Vulkan and DirectX 12. Here we just use Vulkan. In your case, you should change this value to match your graphics card backend. If you use the iOS or Mac operating system, you should change it to the Metal here. So make sure to match your hardware backend. We then use the unsafe code to create a render surface for WinNet window. This surface provides a drawing functionality for the platform supported by the WinNet. We can access the GPU in the WGPU API by calling the request adapter function. Here, the compatible surface field is specified by our surface. You can see here. Once we have the GPU adapter, we can call the request device function to create a GPU device. You can see the features attribute allows you to specify actual features that you may want. For our simple triangle, we don't use any actual features. The device configuration of your machine may limit the feature you can use. The limits attributes here describe the limit of certain types of resources we create. Here we use the default settings which support most devices. The following code is used to configure our surface. Here we first introduce the format parameter that defines how the surface texture will be stored on the GPU. Different displays prefer different formats. Here we call the get preferred format function to get the best format based on display we are using. Inside the surface configuration structure, here the usage describes how the surface texture will be used. You can see the render attachment specifies that the texture will be used to write to the surface defined in the window. Here the width and height are specified by the window size. You can see the size we define by the window here. You can see the size defined as a window size here. Please make sure this width and height of the surface texture are not set to 0. Otherwise, it may cause your application to crash. Next, we load the shader code using the create shader module function. Create shader module function to load our shader code here, shader.wgsl. We just created before. What we have done so far are basic initialization steps, which are common to any WGPU applications, and they don't need to be reset or changed. However, after this initialization, the render pipeline and shader program will be different depending on your application. The render pipeline in WGPU describes all actions the GPU will perform when acting on a set of data. Here we first need to create a pipeline layout. This is useful when we use the GPU buffer. For our simple triangle example, it is just a placeholder because we don't use any GPU buffer here. So you can see binding group layout here, we just empty an array. Because in our example, we just write our vertex and color data directly in the shader code. There's no data pass from GPU buffer to the shader, so this is empty here. But even this is empty, we still need a placeholder to define the pipeline. We then create a render pipeline by calling create render pipeline here. The pipeline requires several attributes, including vertex and fragment attributes. For vertex, here you can see the module we use the shader we just defined here, and set its entry point to VS main because we define the vertex main function we call the VS main. So for the fragment shader we use FS main, which is defined in our shader code. The primitive attribute describe how to we interpret our vertices when converting them into triangles. Here, we simply use the default setting, that is the triangle list. In this example, we don't use depth stencil attribute, so we leave this as none. Inside this event loop run function, we record and submit GPU commands using a GPU command encoder. Here you can see create a command encoder here. You can see that we use this encoder to open a render path by calling the begin render path function. Here we name it as rpath and make it a mutable here. This render path accepts a parameter of type render path descriptor as its option that has several attributes. One is a color attachment. In our example, it just stores the background color here. You can color RGBA. This is the background color. Another attribute is depth stencil attachment, which stores depth information of our render path and the template information. Our triangle example does not need depth information because it is a 2D flat object with no depth. So here we set it to none. Next, we assign the pipeline to the render path. You can see set pipeline to this render path and call rPathDraw function to draw our triangles with 3 vertices and 1 instance here. Note that in order to present the surface texture called frame returned by, you can see we define the frame here. This frame returned by calling surface.getCurrentTexture function. We need to first submit all instructions to the queue of the GPU device. for execution, and then call the frame present method to schedule the texture to be presented on the surface. So in this main function, it's very simple. We first create the event loop and the window using VNet. Next, we call poster block on methods to call our async run function. You can see run function. After running the command, our triangle will be written to the surface and displayed in the VNet window. Up to now, we have finished our programming and explanation. So now we can save this file. Now we can run the following command on the terminal window to create our triangle. So terminal window, cargo run. Okay, here is our triangle with different vertex color, red, green, and blue. You can see the color changes from one vertex to another gradually and smoothly. This is because in WGPU, the color is interpolated over the fragments to produce a smooth color gradient. Now I will end this video here. In next video, I will show you how to create various primitives in WGPU. Thank you for watching.